Hi, hello everyone. Welcome to today's seminar. Today we are thankful to have Andrei Runov speaking to us. He received his PhD from St. Petersburg University. He then moved on to work for the Space Science Institute at the Austrian Academy for Sciences in Graz, and is now currently working as a researcher at UCLA in the College of Physical Sciences and the Department of Earth, Planetary and Space Sciences. Today, Andrei is going to be talking about Magnetotail transients. And with that, Andrei, if you would like to start.
Okay, thanks. I share my screen. Share. Okay. Presentation mode. Hope you see my slide.
Yep, we see your slides now.
Okay, so thank you very much for this invitation. And actually, I'm sorry, I attended maybe a couple or a few of these presentations before, just because it's in conflict with our internal meeting here. Anyways, thank you again for invitation. Thank you all for coming. Today I will talk about Magnetotail transients revisited. So why revisited? Quite a few years ago, I guess, let me stop probably this. Quite a few years ago, I gave a gem tutorial about Magnetotail transients and their influence to the inner magnetosphere populations. It was essentially pre-Artemis era. Now we have a lot more information, mainly from Artemis mission and Themis new configuration. And I guess it's time to revisit Magnetotail transients and see what we learned from new missions since a decade. Well, I will talk mainly about Themis and Artemis data from observational point of view. It doesn't mean that other missions like Geotail cluster and specifically MMS, speaking about new missions, are not important in this context. Quite contrary, it's just I am short in time and cannot really cover all the observations, all the topics which deserve to be covered from MMS and other missions. So I will concentrate mainly on Themis and Artemis. Artemis, as you probably know, is the mission containing two spacecraft orbiting the moon, and with the moon traversing Magnetotail roughly 3 to 4 days every month, every Earth month. And Artemis currently consists from 3 spacecraft orbiting around the Earth with apogee about 10 to 13 Ari downtail. Well, let me start from brief introduction. First of all, what the coordinate system I will use in this talk. This is the geocentric solar magnetospheric coordinate system depicted here with the x-axis toward the sun, z along instantaneous magnetic dipole, and y completing the right-hand system. In this nominal geometry, the Magnetotail current flows from dawn to dusk along y direction, and it closed through the magnetopause. The most important or key region in the Magnetotail is the Magnetotail plasma sheet. which is which sets here on closed magnetic field lines. What is important about the Magnetotail plasma sheet to know that this is the region with actually very weak magnetic field. Equatorial magnetic field, it varies a lot with the distance, but around 20 Re, it varies between 5 to 10 nanotesla. And towards the lunar orbit, it's basically vanished to almost zero. Despite this weak magnetic field, we have very strong magnetic gradient here. And the current density, which is actually magnetic field gradient, varies a lot with the magnetotail activity. It may reach tens of nanoamperes per square meter, which is very, very strong current. Another important thing is that it is high beta regime, meaning that the main energy is in the thermal motion of ions. So speaking about the magnetotail plasma sheet compared to, say, inner magnetosphere, it's high beta regime with weak magnetic field and strong gradient. It's in some sense totally opposite to inner magnetosphere. And many of our ideas how particles behave in the magnetic field, in the quasi-dipole strong magnetic field, are not valid in the plasma sheet, magnetotail plasma sheet, where thermal ions and energetic electrons do not conserve their first adiabatic invariant. So it's very important to keep this in mind. Well, we all grown up with the so-called Dungey cycle. So Dungey cycle is the time cycle started from reconnection between interplanetary magnetic field and the magnetospheric field in the day side, on the day side magnetopause. Then the reconnected field lines, flux tubes, better say, transported toward the tail, reconnected in the tail and returned back. In the Earth magnetosphere, the time scale of Dungey cycle is around 1 hour. For example, Mercury, this Dungey cycle is about a minute. But so again, in the Earth magnetosphere, the cycle of steady state magnetospheric convection is around 1 hour. However, observations since a decade revealed that transport, both energy and flux transport, magnetic flux transport in the magnetotail is quite impulsive, and time scales of these impulses varying between, say, seconds and 100 seconds. So it's 2 or 3 orders of magnitude shorter than Dungey cycle time scale. Moreover, it was found that the magnetic flux transport in the magnetotail is localized in space, special localized within around 1,000 kilometers. So it's tens to 100 ion inertial scales. And these sort of mesoscale spatial temporal phenomena are commonly referred to as magnetotail transients. Here I refer to a pretty old but still very important review paper by Sharma et al. Published in 2008. So if you try to search web for definition of transient, you may find this. So what is transient according Merriam-Webster? So it's passing, something passing, especially quickly into and out of, passing through or by a space with only a brief stay, and most interesting to my mind, affecting something or producing results beyond itself. That's precisely what Magnetotail transients do. Okay, so here is an example of the Magnetotail transients. Shown here are the first panel integrated electric field from Omni. It's basically Magnetotail driving. It's a solar wind electric field driving the magnetosphere, and magnetic field time series with Bz. As you remember, Bz is along the instantaneous dipole. Bz component in red, X component in blue, and Y component in green. So from two Themis spacecraft, Themis D and Themis E, located at around 10 to 11 Re downtail, and corresponding electric field from electric field instrument on the these Themis probes. And you might see it's about an hour, half an hour worth of data. So you may see that despite of this monotonic driving of the magnetosphere, the response in the magnetotail is quite impulsive. We see this set of sudden impulses. You see that Bz jumps from few nanotesla up to several tenths very abruptly. And it's very typical behavior. You may open our Themis website and look through overview plots for every day when Themis is in the tail. You will see this type of behavior. So these are localized, temporally localized spikes of the electric field. Temporally means that they passing spacecraft very quickly. Doesn't mean that it's temporally appeared structures. These are spatial structures passing the spacecraft. So characteristic time of these pulses is about several tenths of seconds. This impulsive behavior known in literature as rapid flux transport events after Shuttle et al. 2001, or dipolarizing flux bundles after Zhang Lu 2013. Actually, the definition of Rfts, sorry, based on electric field measurements, or to be precise, on magnetic field and velocity, so calculated flux transport rate, while definition of dipolarizing flux bundles solely based on magnetic field measurements. Other than that difference, they basically depict the same physical object. Well, if we statistically collect many of these events observed from a variety of geocentric distances from roughly 7 Re down to 20-25 Re, we will find this sort of statistical portrait of the typical Rft, rapid flux transport events, or dipolarizing flux bundle. So what do we see here? It's jump in magnetic field in Bz, often preceded by a dip in BZ, and amplitude of this dip, magnitude of this dip, is larger when the spacecraft is closer, or this dipolarizing flux bundle detected closer to the planet. So colors here represent, excuse me, geocentric distances. Magenta is basically close to a geosynchronous orbit, and green are the most farthest, beyond 15 Re. Black and blue in between. So we do observe this jump in magnetic field, reduction in density, which doesn't depend on the distance, increase, however modest, in both ion and electron temperatures, and the most important to my mind, this peak in electric field. The magnitude of this peak doesn't really depend on the distance. It's a few, up to 5 millivolt per meter electric field. So typical dawn-dusk electric field for steady state convection is 0.1 millivolt per meter. So it's huge, really huge electric field associated with this dipolarizing flux bundle or rapid flux transport events. And interestingly enough, this electric field pulse in temporal space, temporally localized within the typical duration of 40, 50 seconds. So it's tenths of ion gyro period. And if you calculate the scale of that using typical velocity of few hundred kilometers per second, it gives you a couple of Res, or few Re of extent along X. So it's again few tenths of C by omega pi is ion inertial length. It was also found that these dipolarizing flux bundles or rapid flux transport events are quite localized in cross-tail direction. So their width in cross-tail along Y typically around couple of Res, 1, 2 to 3 Re. This plot is from John Lew's 2013 paper, but you may look through early papers by Rumi Nakamura, who used cluster for that and obtained the same spatial scale. So what we're dealing with is actually a very compact object, like shown here. This is the simulation from Joachim Berg model. It's MHD and particle tracing on top of MHD model. So you see this color-coded is electric field, which is basically this. And you see it's very compact object. Actually, several tenths of ion inertial lengths in both directions, in Y and X. And because it's localized, it's very important in sense of particle behavior around. So when this object, this rapid flux transport event progresses towards the Earth, it is localized electric field in frame of reference of particles drifting in the magnetotail. Here you see in this simulation a trace of ions and electrons, test particles. And for example, this ion is picked up by this electric field and transported towards the toward the higher magnetic field, towards the dipole, which means gaining energy. And because it's gaining energy, it drifts across this magnetic structure. So it became quasi-trapped, then drift across and shoot out from the other side with higher energy. You may see how energy gained during this transport towards the dipole. These are ions, I believe, or maybe the both ions and electrons. Same valid for electrons. So that means that this spatially localized electric field, rapid flux transport events, or dipolarizing flux bundles, you name it, continuously convert electromagnetic energy into thermal energy of ambient plasma. So it's actually elementary building block of the magnetospheric activity. Well, now the question is, what determines this cross-tail localization of rapid flux transport events? I stole this slide from presentation by Kevin Ginestretti. There are actually a few scenarios or 4 possibilities how these localized structures may appear. First is the instability of jet fronts. So we have at the beginning very wide jet front, which is unstable to some sort of Rayleigh-Taylor instability, maybe ballooning interchange instability, which produces this localized finger-like structures. This is simulation from Phil Pritchett. Another scenario, we have prolonged all the cross-tail long X-line, magnetic X-line, which produces flows which are channeled, again, basically due to some sort of Rayleigh-Taylor instability, Rayleigh-Taylor type instability to these narrow channels. This is MHD simulation from Wilberger et al. It's LFM. Another scenario actually appeared in hybrid simulations that treat electrons as massless fluid and ions as particles. In this simulation, this is from Yulin 2014, the X-line itself, or reconnection region, or energy conversion region, if you want, is highly localized, again within few REs. And finally, we have kinetic simulation that basically shows roughly same picture as the high resolution MHD. We have long X-line, but localized outflows from this long X-line. So how does it work in the nature? One way to figure out which of this scenario may actually work is to look through tailward rapid flux transport events, which supposedly goes from this X-line, that X-line, tailward. So question is, are they also azimutally localized? And here is the one of examples of this tailward rapid flux transport events. This is from Artemis observations on lunar orbit, so roughly 60 RE down tail. Plotted here is the magnetic field. Again, the main component of our interest, BZ, is in red, and you see deep negative, southward BZ variation preceded by some positive variation. It is embedded into tailward flow, and corresponding electric field way exceed 2 millivolt per meters, which is the threshold for rapid flux transport events. So we do observe this rapid flux transport events at tailward side. So tailward rapid flux transport event. And most interesting here that this electric field pulse is localized within the same 50 seconds. So same temporal and therefore spatial scale as for earthward rapid flux transport events. So do they actually localized in cross-tail direction? The statistical analysis of many of these events, this is from Shanshan Li 2014 paper. Statistical analysis showed that they indeed localized. So if we search for using a pair of Artemis probes, search for correlation length when we observe the same structure on both of the spacecraft, this correlation length quickly drops with the distance and maximizes within 5 Re interspacecraft separation. So again, we have this very localized within few Res tailward flows. So it's actually sort of mirror image of the earthward flows. That actually suggests that localized is the source, which actually close to what we found in the hybrid simulations. Localize the source, reconnection region, or better probably say energy conversion region in the tail. While it localized, why it happens, what determines this this localization within few tenths of ion inertia lengths, the question is wide open. Interesting thing is here that we know from numerous observations that a current sheet thinning, which precedes the bursty bulk flows in the magnetotail, is quasi 1D process, or 2D, meaning that gradients along Z direction and along X direction is much larger than gradients in Y direction. So why then on the Earth these rapid flux transport events are so localized across tail along the Y GSM? We don't know. It's again open question. And what we have, so we do not have actually enough observational information on cross-tail pre-onset current sheet configuration at distances larger than 20 Re. And what we need for that is a fleet of azimutally separated equatorial probes at that distances larger than 20 Re. And the interspacecraft separation should be large enough to address this question. Well, next question is, are these rapid flux transport events or dipolarizing flux bundles associated with the substorm onset? So here I tried to answer this question. Again, I use the same statistics and plot the moments of detection of the rapid flux transport events. So these fronts, dipolarization fronts, against the changes in AL index. And you see that, again, color-coded is the geocentric distances. The magenta is closest, green is farthest. You see from this plot that rapid flux transport observed at distances smaller than 15 Re downtail occur within a minute of AL onset. However, I cannot say from these observations that these dipolarizing flux bundles precede the onset. It's not like that. So this 1 minute problem is still with us. We still are not able to resolve this correctly. Oops, why it jumps? So again, there are many open questions here. So as I told, dipolarizing flux bundles or rapid flux transport events observed within 15 Re, typically observed within 1 minute of AL onset. And what's the association with this between these flow bursts, rapid flux transport events, and substorm current wedge? And here is the plot from very, very old but very important paper by Nagai sensei. It's 1982. These are geosynchronous data showing how the substorm current wedge develops in time and space. So what we typically observed at Geo is more sustained, typically tens of minutes dipolarization, which covers pretty large, pretty wide sector in the magnetotail, up to 10 hours of magnetic local time. So how all these magnetotail transients integrated into this sustained dipolarization, substorm dipolarization, is wide open question. And again, we need a fleet of azimutally distributed, azimutally separated spacecraft now in near Earth magnetotail, in the transition region between tail and dipole. Same question actually valid for energetic particle injections. Again, at geosynchronous orbit, we observe sustained hundreds of seconds dispersionless injections, which covers several hours of MLT. How they related to these rapid flux transport events? Question is open. Some ideas recently were published in this very important, very interesting paper by Christine Gabriels, 2019. Well, to say a little bit more about that, another question is how these dipolarizations, both sustained and transient, influence ring current formation. Do we observe any link, any connection between dipolarizations in the tail transition region? So it's between, say, 7 and 13 Re down tail, and ion injections observed on geosynchronous orbit. This question actually was posed on one of substorm conferences, ICS, when we had these Socratic dialogues, and Martina Gikulidou and Christine came with this question: do we have link between substorms, dipolarizations, and ring current formation? So I asked my friend Mike Henderson to help me with Lennel data, and we found about 40 dipolarization events fulfilling this criteria during main phase of magnetic storms, when Themis, at least one Themis probe was in the around midnight. As you know, probably Lennel spacecraft do not equip are not equipped by magnetometers, but we can use low energy electrons to figure out the magnetic inclination, magnetic tilt angle. And we found that whenever we observe dipolarizations here at around midnight at these distances observed by Themis, we observe dipolarizations at the geosynchronous orbit too. However, only in 10 events from this 40, we found increase in the ion energetic influx of energetic ions at geo. So it's like 30%, and this 30% happens almost any time. So it was shown that roughly 30% of bursty bulk flows reaches geosynchronous orbit. Martina Gikulidou found that only in 30% dipolarizations observed inside geosynchronous orbit associated with ion injections. So the question is now, is there a link between these dipolarizations and what happened, dipolarizations in the tail at what happened in the inner magnetosphere? If only 30% of the dipolarizations contribute to ring current formation with the ion injections, what about other 70? So it's should be steady convection. So again, here is a summary and open questions. In the near Earth magnetotail dipolarizations do not necessarily lead to ion injection at geo. So what's the key ingredient we miss? It's open question. Again, we need a fleet of azimuthally distributed spacecraft in the tail transition region to answer these questions. We know that dipolarizations in the near Earth tail modulated by these dipolarizing flux bundles, rapid flux transport events, wedgelets, you name it. However, we do not find any statistically significant flux variation correlated with this with Dfbs and Rfts observed by Themis. So why? Does that mean that again these transients are integrated in the tail dipole transition region to more sustained dipolarization? We do not understand physics of that. Next question, what's the fate of energetic particles that drift away flankward and do not reach geosynchronous orbit? Do they contribute to particle ring current? And they, of course, redistribute the azimuthal pressure, the thermal pressure produced azimuthally azimuthally localized pressure enhancement, which leads to a formation of field-aligned currents. It should affect MI coupling. So again, we don't know how observationally how it works. Again, for that we need not only a fleet of azimuthally distributed spacecraft in the tail dipole transition region, but also a fleet of polar orbiting low orbit probes similar to POSE, or I can't resist to mention our own UCLA Elfin spacecraft, which equipped by magnetometer and energetic particle detectors to remote sense the magnetospheric configuration and field-aligned currents. And of course, we cannot do our data analysis, especially including a fleet of many spacecraft, without models. And these models needed to address these questions should resolve energy-dependent drift, at least ion drifts, to address all these questions. So I don't know how I'm doing in time, but actually I am done with my presentation, and thank you all for your time, and I hope you all join me with this appeal. Thank you.
Thank you, Andrei. And thank you for the sentiment afterward. I think that's really important at the moment. We do have a couple questions in the chat. We do have a comment by Larry Lyons. It's quite long, so I'll leave you to read it and others to read it. We also have an open question from Stephen. I'm not able to answer it, but if anyone can answer it in the chat, that would be really helpful.
Can I monitor a chat?
Yeah, so the question is an outlier question regarding GICs. So if anyone is able to answer that, that would be really helpful. So in terms of questions, we have a handful, Andrei. Our first question comes from Steve Milan. On slide 2, your table said that the plasma sheet thickness is 1 to 2 Re. But if you look at the closed magnetic field region in the Sengenenko models, it's about 10 times thicker. What's the discrepancy between the plasma sheet thickness and the closed field line boundary in the Sengenenko models?
Yeah, it's a very good question, actually. The plasma sheet thickness and current sheet thickness are actually two different things. So plasma sheet thickness doesn't vary super much. So it's mainly, as Steve correctly mentioned, it's here the width between open blue field lines and red closed field lines. It's typically again it varies with activity. When low loaded, plasma sheet tends to be thinner, but its thickness is several thousand to 10,000 kilometers. However, the current sheet thickness is totally different thing. It's the gradient, the region when magnetic field change the direction quickly. And this current sheet thickness varies in very large range, and it's typically embedded into more thicker plasma sheet. Again, we know more or less how the current sheet thickness, why current sheet becomes thinner and how this current sheet thickness depends, say, on magnetic pressure in lobes. But there are many open questions still, how the current sheet forms and why it is so stable at the growth phase. I don't know if I answer, Steve, your question correctly.
I'll let Steve follow up and come back to it if not. Andy Smith has a question on slide 6. The Rfts and the Dfbs, they seem to be concentrated between about 9.5 and 12 Re. Is this due to the spacecraft sampling or the spacecraft orbit, or do you generally just observe more dipolarization flux bindings in that region?
Actually, if you look here, we observe these dipolarizing flux bundles or rapid flux transport events all the way when we had Themis spacecraft from 25 Re down tail up to synchronous orbit. Just because of orbits, we have way more sampling in the near Earth Magnetotail, is black and magenta, compared to larger distances. But it doesn't mean that this phenomena appeared only in this region. No, as I showed, you may observe earthward traveling dipolarizing flux bundles up to 30 Re here, and tailward traveling tailward counterparts of them at lunar orbit.
Excellent, thank you. We have a couple questions from John Hadusik. On slide 9, you showed BZ turning positive and then negative, but earlier you showed BZ negative, initially turning negative and then going positive. Right. Does this mean BZ can point in either direction during an RFT?
Well, in this case, it's tailward traveling rapid flux transport events. So it is associated with this long and strong southward, so negative BZ variation, while earthward traveling rapid flux transport events associated with northward turn of magnetic field, which shown here. So it's positive delta BZ, and they are embedded into earthward flows. So in this sense, this tailward rapid flux transport events are like mirror images of their earthward traveling counterparts. That again drive us thinking that they probably came from the same localized source. So with the tailward flows with embedded negative BZ traveling downhill towards the tail, and northward turn of magnetic field, northward BZ component embedded into earthward flows towards the dipole.
And so a follow-up question, on slide 12, how do you identify a substorm from substorm onset from AL?
Oh yeah, that's a that's a tricky question. Yeah, everything which about substorms is somewhat tricky. So here, what I did, I simply used Omni AL and look for beginning onset of negative bay, of negative turning. it's rather crude, I would say. So probably this 1 minute problem is a problem of our observations, not really physical problem. But it's still there, at least in this database. So again, I used onset, so time of dipolarization front. So this sharp BZ arrival to the spacecraft, and time it with respect to onset of negative Bay in AL index.
Okay. So our next question comes from Joachim. Around slide 10, you showed that the tail word Rfts and dipolarization bundles changing from north to south. What is the total BZ? Does this also indicate the passage of an O-line? And how frequent are short duration Rfts compared to smoother transient O-line plasmoids?
Yeah, it's actually a very good question. We tried to analyze separately what we think were like plasmoids. So maybe sort of closed O-type magnetic configuration and these dipolarization fronts, but it's a bit difficult to do observationally. What is nice in these dipolarizing flux bundles with this sharp dipolarization front, they're easily detectable. They're easy to time. But O-line type of structures, we do observe them, but it's very difficult to because they, as Joachim said, they are smoother. It's difficult to make timing around them. So I cannot really answer right now how well what type observed more often. Maybe just because these anti-dipolarization fronts or tailward Rfts way easier to detect. I have to come back to this paper by Shan Shan. She probably had the answer at that time. I just do not have it on top of my head.
Okay.
Sorry, Joachim.
So next question is from Elizaveta. Do you see any connection between dipolarizations in the 5 to 7 RE region with the development of the ring current or the outer radiation belt?
Well, there are two types of questions here. First about ring current, then next about radiation belts. It's actually interesting story. As I told, if I'm concentrating on ions and think about a population of ring current during main phases of storms, we found that only in 30% the dipolarizations observed in the tail dipole transition region associated with increase in ion energetic fluxes in 3 consecutive energy channels by SOPA on Lanel. For electrons, actually, situation is different, as it has been shown at least by Drew Turner and some others, that typically any dipolarization observed close to geo associated with electron injections. So electrons are easy to inject than ions, just because they are lighter, their gyro radius is smaller, and they confined in these magnetic structures. Basically with these magnetic structures transported towards the inner magnetosphere. With ions, it's more tricky. Ions larger, they have larger gyro radius, and they do not obey their first adiabatic invariant. Hope I answered.
So Steve has a follow-up question. He has a comment regarding the other regarding his first question, but I'll let you read that. I can also email it later on. So he notes that this is a slightly cheeky question. Are Rfts and Dfbs the same as Bbfs?
No. I'm not going to details here. So if you look through classical papers by Vasilis Angelopoulos, how bursty bulk flows are defined, you may see that bursty bulk flows actually sort of enveloping structures, which contains many of these dipolarizing flux bundles, or may contain many of them. It's actually interesting how nature works. Like I showed here, okay, I did not show velocity for first moment here, second moment. But if I plot velocity around, you may see that the earthward velocity actually envelops all these magnetic structures. So bursty bulk flow will contain all these three jumps here. However, if you think about what is important in sense of interacting with ambient particles, it's electric field, flux transport. And flux transport is actually localized within this very smaller than Bbf structures. So Bbf may contain, like in this case, several to many of these dipolarizing flux bundles. In this sense, as I said here, this rapid flux transport events is actually elementary structure. It's elementary building block of magnetotail activity.
Excellent, thank you. So we have one more potential question. I'm not sure. Joe, your hand is raised. Did you have a question?
Oh, yes, I do. I have a question and a comment. Thanks. Thanks, Andrei, for a really nice talk. I haven't paid attention to Bbfs and transients in the tail for a long time, but there used to be a lot of talk about the role of entropy. Are those theories still valid, and is entropy something that's worth thinking about for these things?
Yeah, it's very interesting question. I'm not sure. Well, maybe let me see if I have. No, unfortunately not. I do not have slide with entropy. Well, when we're talking about entropy, we should be clear about meaning, whether we're talking about specific entropy or flux tube entropy,
right,
of entropy function. These are two different things. And most interesting is then these Bbfs or dipolarizing flux bundles. They are associated with drop in density. So they are bubbles in sense, right? Meaning that the flux tube entropy decreases. However, temperature goes up, and the specific entropy increases. This is kind of tricky thing here. Again, specific energy increases, but flux tube entropy decreases on these structures.
Okay. I have a quick comment I want to make about ion injections at geosynchronous versus electron injections at geosynchronous.
Yep.
When Bob Nemzek and I, a long time ago, first did our substorm counting at geosynchronous, we used the old Los Alamos satellites that had the CPA instruments on them rather than the SOPA instruments. And CPA had an actual separate ion detector from the electron detector. And on those instruments, it was much easier to see injections in the ions than it was in the electrons.
Mm-hmm.
MPA, or the SOPA, uses the same detector for ions and electrons, and the ions aren't very clear on the SOPA instrument.
Right. Yeah, I agree with that. It's still, I'm not sure that this is the answer why we do not observe ion energetic injections associated with any dipolarization.
Mm-hmm.
I think what is important to understand.
Certainly there will always have been Bbfs without injections at geosynchronous. I mean, during steady magnetospheric convection events, you have Bbfs like mad, and you have
first
no
of all,
injections.
It was shown many times in different studies that only about 30% of Bbfs, these dipolarizing flux bundles, bursty bulk flows, whatever, are able to reach geosynchronous orbit.
Right.
Again, thinking about entropy, flux tube entropy. So it's underpopulated flux tube, which propels earthward until the point when the entropy inside this flux tube is becomes comparable with entropy, flux tube entropy outside. Then it stops. Interesting question, what happens with particles there? So they drift away. About ions and electrons, we found actually even with simulation, Joachim Bern's simulations, that ions are more sensitive to electric field rather than magnetic field variations. I mean, to accelerate or energize ions, make the ion injection, you need azimuthal electric field. So only those dipolarizations which are associated with inward flux transport are associated with ion injections. However, many of dipolarizations are not going anywhere. You know, it's the bundle stops, the field line currents are created, and then it's basically a balanced, sustained situation. It doesn't, we have dipolarization. We have dipolarization in the near Earth tail. We have dipolarization at geo, but there are no injections, ion injections, right? Just because we do not have electric field, azimuthal electric field, which moves or transport ions towards the inner magnetosphere.
Thank you.
Thank you.
So I think Joachim might have a follow-up regarding the entropy.
Yeah, you guessed right. I think entropy, and I'm talking about the field line entropy content, may play a role in how far or how deep depleted flux tubes penetrate close to Earth. So that might play a role in whether flux tubes get all the way through geosynchronous or inside or not. So it might be worthwhile studying the entropy content, although that's a difficult problem, for those events that are observed by Themis, but not on geosynchronous, by geosynchronous injections.
Right, yes. First of all, again, by entropy, you mean flux tube entropy, right?
Correct.
Yeah. So here,
So
well,
we have to rely on this approximate formula by de
Right,
Grolf or so
right.
to
So-
estimate that. Yeah.
Yeah,
Mhm.
we did it. Actually, I did it in one paper. It was fight with referee, I would tell you. Just because we use this de Grolf formula to calculate flux tube entropy in the situation of fast flow, which is basically incorrect. But you know, there's nothing better yet.
Mhm.
We may use, and it was used at least in a couple of publications, the sort of Tsiganenko type model, but adopted model, corrected with respect to actual magnetic field observations to calculate entropy. It's possible. Another problem is that, again, we do not have magnetometer at LANL. So we should rely on MPA, so low energy electron data, to figure out what's going on with the magnetic field.
So we have one final question that's a follow-up to Steve's, and it's from Andy Marshall. He's seen another term, flux rope type dipolarization front. Would that be more similar to Rfts and Dfbs? Or have you heard of this term?
Flux rope type dipolarization fronts, I'm not sure what exactly Andy meant by that. We typically, well, we observe plasmoids or flux ropes traveling tailward, but what we observe on earthward side, are mainly these quasi 2D planar structures. We do not actually observe what one may call flux rope. There was a paper by Viktor Sergeyev, was the second author, I forgot the first one, who tried to reanalyze Jim Slevin's statistics of earthward traveling flux ropes using energetic about kV electrons as a tracer of magnetic configuration, and they found that in majority of these cases that we thought that we saw earthward moving flux ropes, they in fact dipolarization fronts. So there are no confined electron population confined within closed magnetic field like flux rope. So
yeah, it's the
to be honest,
the main characteristic that I remember seeing about those was the slight dip in BZ before the dipolarization front, and it was earthward traveling like the Slavin paper you're referring to.
Right. But it's well, I guess physics of this deep, BZ deep ahead of the dipolarization front is different. If you think at the moment in terms of electric current, you have the vertical electric current sheet, right? And magnetic signature of this current will be bipolar variation. However, it doesn't mean that you have an island or flux rope. It's just a magnetic signature of the upcoming vertical current.
Okay.
See what I mean?
Yes, I do. Thank you.
All right, thank you, Andrei, for a wonderful talk and a lively question period. Our next
Thank you.
seminar will be next Monday, and it'll be our next set of early career speakers. We'll have Connor O'Brien and Julie Lu speaking. Apologies. You can find their abstracts, a link to their abstracts and to their title in the chat, and that'll also be sent out on Sunday in the next reminder. I hope everyone has a wonderful week, and I hope to see you next week. Thanks again, Andrei.
Thank you. Bye-bye.
Bye-bye.